Hello, my name is Richard Jung, and I will be solving problems 17 and 70 of the Practice FE and providing context to each one. Due to the nature of the FE, this additional context is wholly unnecessary. However, I think it sheds light on hidden stories that relate the otherwise dry presentation of an engineering concept to an utterly fascinating, real-world context. So let's start. Problem 13 states, the mass of sulfuric acid required to produce 1,000 milliliters of 0.25 N sulfuric acid is most nearly. So here we are asked to determine the mass of H2SO4 given a desired volume and concentration. We can do this by determining the molar mass, dividing by 2 because it's a dibasic acid, and using use of our principles, where 1 N of sulfuric acid means there's 25 grams of sulfuric acid dissolved in 1 liter. We can divide this value by 0.25 and we get approximately 12.3 grams of sulfuric acid. So the correct option is A. Now, we would normally stop here. If you were taking the FE, you should stop here and move on to question 18. But today, we have time. We can explore the deeper context of this problem, its hidden story. Sulfuric acid is used in countless reactions, both organic and inorganic. It runs heavy industries the world over. Without it, modern civilization would surely collapse. Billions of dollars have been invested in technology to synthesize, transport, and utilize this single chemical. In fact, there are entire assemblies dedicated to diluting this one acid, as we did in the problem. There is a whole world of engineering and science that is glossed over in this problem, so let's first find out where this all begins. This man's name is Johann Glauber. In the 17th century, this German-Dutch chemist first prepared sulfuric acid by burning sulfur together with potassium nitrate in the presence of steam. As the potassium nitrate decomposes, it oxidizes the sulfur to sulfate, which combined with water to produce sulfuric acid. The next man on our list is John Roebuck, who in 1746 began producing sulfuric acid in lead-lined chambers, which are stronger, less expensive, and could be made larger than the glass ones that previously used by Glauber. This lead chamber process allowed the effective industrialization of sulfuric acid production, with several refinements remaining the standard method for almost 2 centuries. However, the greatest improvement was made in 1831 with the British vinegar merchant Peregrine Phillips, who patented a far more economical process for producing sulfuric acid. Now is called the contact method, the contact process. And the entire world supply of sulfuric acid today is now produced through the contact process. Now, sulfuric acid is inextricably linked with various heavy industries around the world, the main being phosphate fertilizers, without which we would not be able to sustain an agriculture production as high as we are doing today. The other is metal processing, such as plating, and goes into high performance applications. And most importantly is petroleum. The petroleum industry uses sulfuric acid extensively in order to process and purify various petroleum and crude oil products. However, there is more to sulfuric acid than its modern day use. It is so useful, in fact, that it closely tracks major events in human history. Let's look at the US as an example. Sulfuric acid production dropped after the American involvement in World War I and open trade resumed. The stock market crash of 1929 further stagnated growth, which was restored at the outbreak of World War II. As the U.S. entered the war, the economy was rapidly brought up to full production capacity. The post-war period saw the greatest economic growth in America's history, and this was reflected in ever-increasing sulfuric acid production. This trend continues today. Now we will look at problem 70. While this problem is more conceptual, it only scratches the surface when it comes to a real-world application. Problem 70 reads, if an aluminum crimp connector were used to connect a copper wire to a battery, what would you expect to happen? Now, on the outset, without any prior chemistry knowledge, this would seem like a guessing game, but the solution is quite simple. In order to solve the problem, you need to know about the concept of standard reduction potential. This essentially measures the tendency for a chemical species or element to reduce, or lose electrons. This affects chemistry when it interacts with other species, in this case, another transition metal. Since both copper and aluminum are transition metals, they will behave differently when electric current passes through them. Standard reduction potential helps us to understand this discrepancy. Since the standard potential for aluminum is lower, this means that it is a stronger reducing agent. In other words, it is more likely to corrode since it is more likely to lose electrons or oxidize. Thus, compared to copper, only alumina will corrode in the presence of an electrode. Thus, option B is correct. Now let's move on to a fascinating real-world example of how this property of standard reduction helps save countless billions in rust and corrosion damage. These are called sacrificial anodes. They are attached to ships and help combat the oxidation of the structure bearing hull. Corrosion is one of the greatest enemies of the ship and its machinery. From stern to bow, iron is one substance which is used in great abundance. Unfortunately, it is also the most corrosion-prone material when it comes in contact with the salty air and water. The outer body of the ship, mainly the hull, is continuously in contact with water, making it even more vulnerable to corrosion. Sacrificial anodes work on the principle similar to electrolysis, according to which if an anode and a metallic strip are dipped in an electrolytic solution, the anode electron will dissolve and deposit over the metallic strip and make it a cathode. This is what you see on the zinc anode. In the case of a ship, seawater acts as an electrolyte and transfers the electrons from the anode by oxidizing it over the steel plate and making a protective layer. If the metal is more active, it will be easily oxidized and will protect the metallic compound by making it act as a cathode. The anode will corrode first sacrificing itself for the other compound, and it is thus called sacrificial anode. This is what you see as a deposit on the anode itself. This property is taken advantage of whenever corrosion is highly detrimental to the use case environment and certain protective measures, such as alloys and paints, are impractical or cost prohibitive. As a result, zinc is a common material for sacrificial anode, as it is cheap metal. In addition to ships, such cathodic protection measures are used on oil rigs, plumbing, underground pipes, and steel rebar.